So now we know what an eigenvalue is. It's a number lambda, such that lambda times the identity minus the matrix we care about is singular. And we've seen a few basic properties of eigenvalues. The idea is that throughout the rest of the semester, as we learn new concepts, we'll see how those new concepts tell us about the theory of eigenvalues. The last thing I want to end this lecture on is one concept called geometric multiplicity. So the geometric multiplicity of an eigenvalue lambda is referred to notationally as gm sub a of lambda. And this is defined as the nullity of lambda times the identity minus a. Remember, if lambda times the identity minus a is singular, that's the same thing as saying lambda is an eigenvalue. And, well, being singular means that the nullity of that matrix is greater than 0. The geometric multiplicity is whatever that number is. So here we have an example of a matrix A. I went ahead and verified that the number lambda equals -2 is an eigenvalue. I looked at the characteristic matrix where I replaced the variable with lambda equals -2, and so that's -2 times the identity minus a. I did my row reductions, and I got a singular matrix. So -2 is an eigenvalue of this particular a. And what is the nullity here? Well, I see in my reduced row echelon form that I have 2 non-pivot columns. So that tells me that the nullity equals 2. So here, what we've illustrated is that the geometric multiplicity of -2 as an eigenvalue of this particular a is equal to 2. Let's do another example just to illustrate the point. Here we have another 3x3 matrix A, and someone is telling us that the eigenvalues of this matrix are -2 and 5. So this is a particular matrix, and I happen to know that this matrix has exactly 2 eigenvalues, lambda equals -2 and lambda equals 5. How do I figure out the geometric multiplicities of these eigenvalues? Well, what I need to do is I need to look at the nullity of the associated characteristic matrix. So for the geometric multiplicity of -2 as an eigenvalue, I need to look at -2 times the identity minus a, and I need to figure out whatever the nullity of that matrix is. I know it's guaranteed to be a number bigger than 0 because this characteristic matrix is required to be singular in order to even say in the first place that lambda equals -2 is an eigenvalue. So I know that I won't get 0. The question is, what number will I get? And I did the row reductions here, and I found that the geometric multiplicity ended up equaling 1. That is, the nullity of this characteristic matrix is 1. What about 5 as an eigenvalue? Well, to figure out the geometric multiplicity of 5 as an eigenvalue of A, I need to look at the nullity of the associated characteristic matrix. So I need to take 5 times the 3x3 identity and subtract off A and figure out what the nullity of this matrix is. I plugged this one into a computer and figured out that the nullity is equal to 1. So the geometric multiplicity of 5 as an eigenvalue here is equal to 1. So the way we would discuss this example is we would say, here's a perfectly good 3x3. I was lucky enough for someone to tell me that the eigenvalues of this matrix are -2 and 5. And then I went ahead and verified that the geometric multiplicity of both of the eigenvalues is equal to 1. Let's conclude our discussion about geometric multiplicity by saying something about bounds for geometric multiplicity. Our first real theorem about eigenvalues here says that if you give me the complete list of eigenvalues, lambda 1, lambda 2, up to lambda k, what we can do is we can look at all of the associated geometric multiplicities, and we can add those numbers up. Well, on the low end of this spectrum, we know that each geometric multiplicity is at minimum equal to 1. So we know that we'll never get a number less than the number of eigenvalues. In this case, I'm using the number of k, the number equal to k. So if we sum the geometric multiplicities, we'll never get less than k, which is the number of eigenvalues here. And it also turns out that you'll never get a number bigger than the size of the matrix. So if you have all of the eigenvalues and you sum all of their geometric multiplicities, you'll never get a number bigger than the size of the matrix. And one consequence of this theorem says you'll consequently never have more than n eigenvalues. So if you have a matrix that's 5 by 5, you know you can't have 6 eigenvalues because 6 is too many. You might have just one, but you'll never have more than 5. So here's an example. Here we have a 3 by 3 matrix, and this 3 by 3 matrix happens to have only 3 eigenvalues, or exactly 3 eigenvalues. Well, one thing I know about the geometric multiplicities is that if I were, I could go through and calculate them individually, but I also know that if I sum them all together, I'll never get a number less than the number of eigenvalues here, which is 3, so I can't get a number less than 3. But 3 is also the size of this matrix, so I can't get a number greater than 3. So what I'm doing here is I'm summing 3 positive integers that equal 3. This immediately tells me that they're all individually equal to 1. So here we're in a scenario where we don't have to do any work to find the geometric multiplicities, because I know when I add the geometric multiplicities together, I never get a number bigger than 3. I'll actually go back 2 slides here to point out that this is not always the case. So here in the example we did previously, we had a 3 by 3 matrix with only 2 eigenvalues. And when you summed those geometric multiplicities together, you got 2, which is less than 3. So the bounds we're giving in our theorem here will not always be achieved on either end. So sometimes you'll get the geometric multiplicities summing to equal the size of the matrix. Sometimes you'll get the geometric multiplicities summing to not equal the size of the matrix. Okay, so that's all I want to say about eigenvalues for now. This is going to be a subject that's sort of woven throughout the rest of the course. So I want us to have a very solid foundation in terms of like what these concepts mean.